All right, so cation exchange capacity is all about the idea that nutrients need to find a way into the plant roots. And it uses positive and negative charges to do that. So I mentioned that clay particles have typically a very specific charge. Do you guys remember what it is?
Negative.
It's a negative charge, right?
Electrons.
Yeah. So there tends to be more electrons on the outside. So they're an ion, and they have too many electrons on the outside of their little atoms. Okay, and so what they're doing is stealing electrons from other atoms. Okay, and the whole idea is that if they have a negative charge to them, which is the case in most soils here in North America, not always the case, but mostly the case. They have a negative charge. What are we hoping for nutrients if we want to attract that nutrients to the soil particle? What kind of charge would nutrients have?
Positive.
It would be positive, right? And so we call that a cation. And I always think of a cation. Cation. And if you remember, that kind of looks like a plus sign, right? The T. I always remember that cations have a positive charge because the T looks like a positive sign. Okay, and of course the opposite of that is anions, and anions have a negative charge. Okay, and the soil particles are surrounded by these anions with a negative charge on them, and therefore they attract these cations. Okay. So that is the whole basis of our lecture today, is the difference between those cations and anions. There we go. Here we go. All right, so let's define what cation exchange capacity is. So here's our definition. Very important to take notes today. So what we've got going is cation exchange capacity, CEC is what we usually call it, is the total amount of positively charged ions in nutrients, what we call cations, that the soil can hold and exchange. Okay. And again, we're really talking about nutrients, nutrients that the soil can hold on to or exchange. And so it's a pretty important little thing going on for us here as far as the soil is concerned. Without this, plants just can't survive, and of course, without plants, on this earth, nothing works, right? It just doesn't work for us. So we have two ways of measuring that, and it's really the one that we really use. This is the metric version. It's probably what we should use, but for whatever reason, most of the time we use this, what we call milliequivalents per 100 grams of soil. Milliequivalents per 100 grams. So we typically use this one, not so much this one. This is centimole of positively charged ions per kilogram. And I almost never see that one, but it is used sometimes. Okay, milliequivalents per 100 grams. That's what we're gonna predominantly focus on. I'm thinking our lab next week is going to have something to do with this because it's such an important topic. So just note that those are the two types of units that are used in cation exchange. Okay, let's so okay, why soils hold cations? Well, it's all about what I just mentioned. I'm not going to rehash it too much. Soil particles typically have negative charges and attract positively charged nutrients. And that's mostly found in clay, mostly. So we're talking about maybe in sand 4 to 5 milliequivalents of nutrient holding capacity compared to like anywhere from 30 to 50 milliequivalents in sand. So it's just magnitudes of orders of just so much more can be held on to. And mostly it's just because there's so much more surface area available on a really tiny particle versus a big particle in the same amount of space. And we've talked a little bit about that. At the end of class, we'll watch a brief video on that just to remind us. So mostly clay minerals. Another big one is organic matter, also tends to hold on to them. But organic matter doesn't necessarily need to be positive or have a negative charge to it. So not always reliable. Here are some of those more common cations out there. A couple of things to note on these. First of all, calcium, magnesium, potassium, ammonium, hydrogen. Hydrogen is huge. In fact, plants use hydrogen, these positively charged hydrogen ions, to cause the plants to give up their nutrients and pull them in. So they donate them to the soil so that the soil will give up their nutrients and then they can pull them in. So it's kind of a trading hydrogen ion, positive cation for the nutrient. And of course, aluminum as well. Now notice when you look at these symbols, these chemistry symbols here, some of them just have a plus. Some of them have a 2 plus, like those two, and then some of them have a 3 plus. Soil will hold on to them, onto those ions more strongly the more electrons are available. So the 2 and the 3 plus, their soil's holding on to those more strongly. They're not going to let those go. And so the plants have to donate more hydrogen ions in order to, they have to pay more out in order to get soil to let go of those ions, those cations. So that's kind of important to note. So the greater the number, the more strongly they're going to be holding on to those cations, the soil is. Okay, where is this all happening? It's called exchange sites. Exchange sites occur on the soil particle, on the clay particle. And so now we don't want clay to hold on to them permanently. We really want them to be able to let go of them in order for the plant to let go of them. And so the clay, the nutrient is often surrounded completely by water a little bit. We'll talk more about that later on. But that little tiny layer of water makes it so that the soil particle isn't holding on to them permanently. They're not permanently bonded. Otherwise, it would be way too hard for plants to get them away from the soil particle. So these are negatively charged surfaces on the soil particle. that are holding the cations. The cations are loosely held and can be exchanged with others in a soil solution. Again, solution is referring to water. Okay, makes it a way easier. If it gets too dry, it's not letting go. It's going to bond those particles together. Okay, so let's look at an analogy. Soil equals a parking lot. Cations are equal to cars. Cation exchange capacity is the number of spaces in a parking lot. So we could go out to the parking lot that's clear right now, count up all the spaces out there, and know how many cars that are in there. Same with the parking lot that's right out here, right? And so we could totally do that if we wanted to. And that would be the cation exchange capacity for that soil, or the number of cars, the car holding capacity for our parking lot. So high CEC means that the soil can hold more nutrients. Okay. Low CEC means that it can hold low nutrients. Now, does that mean that high EEC means greater growing capacity for that soil? It's a trick question. It means no. The trick question is, it actually doesn't matter. It just matters how frequently the soil is replenished with growing capacity, with that nutrients. So, for example, in the rainforests of Brazil, they have terrible CEC, but they got lots of plants, right? Right?
Yeah.
Tons of plants in the Amazon rainforest. Have a terrible CEC, but because plants die so quickly and there's so much water, it's able to replenish that soil very, very quickly. And so even though it has low CEC, it can still grow lots of plants because of the other conditions that are present. Same with agriculture. You may have a soil that has really low CEC, but as long as you fertilize a little more frequently, maybe not quite as much fertilizer when you do, because it's not going to hold on to it anyway. But just a little more frequently and less, then it can still grow, right? Okay. So keep that in mind as we talk about that. High CEC just means you may have to fertilize a little bit more and less often, but it can be somewhat of a benefit. Okay, what are factors that are going to affect CEC? Obviously, soil texture, right? Because clay is the biggest holder of nutrients. Now, we automatically would think, why don't we have tons of clay in all of our soils? We would want clay in our soils. Obviously, soils are a problem in other situations like soil compaction and infiltration. Don't allow water to move through it very easy, and it's really hard soil. So it's better if you have a nice mix of soils, that loam soil that we've talked about. But you want some clay in there in order for that CEC to occur. So the clay mineral types, so we've talked about the different types of clay minerals a little bit yesterday, and they can be, or not yesterday, on Monday. That ratio can certainly play a role in the different types of play a role in the factors for CEC. So organic matter content, as you know, again, organic matter itself tends to have a negative charge to it, and also is a great component of CEC. And since organic matter is typically made out of carbon and all of the other nutrients, it's a nice addition to the cation exchange capacity. And soil pH. Soil pH is going to influence whether or not a plant has the ability to pay the price, which is going to be those hydrogen cations, the currency of paying the hydrogen If the pH is too high or too low, it might make hydrogen ions either more or less available for the plant. Okay, or if someone else is paying lots of hydrogen ions, which is what pH is. There's the H right there, concentration of hydrogen ions. Someone else is paying more hydrogen ions. The plant may not be able to get it at all because someone is there's too much of it in solution around the plant already. So I've already kind of said this, but sand has low CEC, uh, four 4 to 6 milliequivalents. Silt is like 10 to 15 ish, and clay is 50, 30, 50, 60 milliequivalents. And so clay just has lots of surface area and therefore lots of negative charge. And I have said that in North America we have a lot of negative charge in our soils. But if you go down to like Cuba or the Bahamas, some of those islands in the Caribbean, actually their soils tend to be more on the positively charged end of things, which is kind of weird, right? Since most soils aren't, their soils tend to be more positively charged. And so you have to rely on different nutrients there, which is kind of weird. So, all right. So we mentioned, and I don't remember if I actually said these words on Monday or not, but kaolinite has low CEC, low cation exchange capacity. That had the ratios from 1 to 1 that we were talking about on Monday. Illite, moderate CEC, and smectite has high CEC. Okay. I've already said this, so just to reiterate it, organic matter has very high CEC, which is why soil, I've said it like 10,000 times already this semester, the solution to nearly every soil problem is organic matter. And if you get nothing else from this class, I hope that you will remember organic matter, organic matter, organic matter. Almost always is the solution to a problem. There is occasionally exceptions to that rule, but I got a good story about that. I'll have to tell you sometime, not today. So yeah, add organic matter. Okay. I mentioned soil pH and CEC. CEC is increased as soil pH increases. Again, it has to do with the hydrogens that are available. As hydrogen increases, as pH, as pH is on a scale from 0 to 14, right? And at 7, what's at 7? pH of 7? Nope, it's right in the middle. What's at 7?
Pure water.
Pure water is at 7, right? And then anything under that is acidic. And typically what we are talking about as hydrogen ions increase in concentration, that means that you're getting more and more acidity. Okay. On the opposite end of that, as you go up from 7 to 14, you're getting more and more basic. And your concentrations of hydrogens are getting less and less and less. Okay. So, yeah. Higher pH creates more negative charge sites. So, okay. Oh, I've already mentioned this. I forgot that it was on there. But there you go. There's the numbers if you need them. You can see how much more organic soils are, even from clay soils. And this is in centimoles, but milliequivalents. Okay, would be roughly the same types of ratios that you would see. Okay, base saturation. This is a term that you're going to want to remember. Base saturation. Base saturation is the percent of cation exchange occupied by calcium, magnesium, potassium, and sodium. Okay, so that's the definition of base saturation. That's an important term when it comes to the cation exchange capacity that you're going to want to remember. The higher the base saturation often indicates more fertile soils. And it's simply just saying, hey, you can hold more cation exchange, right? You can hold more of these cations as a result of your higher CEC levels. And we just call that base saturation. So a really good way to think of it, kind of an analogy, is how much can a sponge hold of water, right? A sponge that can't hold very much water isn't a very useful sponge, right? But if a sponge can hold lots more water, then it's got, really good, strong water holding capacity. That's a pretty dang good sponge. And so you think of it kind of that way. Base saturation just is a soil that can hold, it's a nutrient sponge that can hold more of these cations that are available out there. Okay. So what's the most limiting nutrient besides water? Soil nutrient? N. What's N?
Sodium.
And A is sodium.
Nitrogen.
Nitrogen. So nitrogen is the most limiting nutrient. Nitrogen in and of itself, by itself, doesn't hold on to soils very well. Not very, very good. It actually has to be in a different form, like something called NH4 ammonium, or NH3 ammonia. Those two in those forms then become a cation that can be held onto soils. But you notice that it's not up there as one of those part of base saturation. And that's because it is very water soluble. It just runs off in water. And it doesn't, it just leaches out of the soils very well, very quickly. And so the soils don't hold on to the nitrogen molecules very much. So these are the other ones. Potassium's a big one. It's one of the big three. And so anything that can hold on to potassium for a little bit of time is going to be another important molecule. Okay, it's probably right behind nitrogen as far as importance. That's what the K is up there. So. All right, so obviously, kind of as we draw closer to the end of this presentation, in agriculture, understanding your soils and its ability to hold nutrients is pretty important because it's going to determine how frequently you fertilize them. Most of our cotton farmers around here have figured out their fertilizing strategies simply based on practice, right? They've tried a few things out over time. They've been around. They've figured it out. Some of them have gone the extra mile and got their soils sampled and found out what their cation exchange capacity is, and then adjusted their fertilizing appropriately. Most of them are probably adding way too much fertilizer to their soils. And they could probably save some money simply by fertilizing a little more often, but with less fertilizer. So that's all about fertilizer efficiency. We've talked about soil fertility and buffering capacity, pH buffering capacity with that. Okay. So environmentally speaking, this is a really important thing, because soils that don't hold on to their nutrients means that a lot of nutrients gets lost in water. Okay. So our cotton fields are flood irrigated around us, and that means water is coming in, being used by what it can, and whatever isn't getting used gets flushed out, right? That's going to be a lot of nutrients. A lot of nutrients are going to get flushed out if it's not being picked up by the soils and held on to the soils. If they're exceeding that base saturation, soil can't hold anymore, so it's just going to go down and get lost. So why is that bad? If the nutrients it's just going to deposit it somewhere else. Can you tell me why too much nutrients in the water can be bad? Any thoughts? Why is too much nutrients in the water not a good thing, especially if it's running off and going downstream? What's downstream? Ocean eventually, yeah. We'll talk about that in a moment. That's a really good one. But let's talk locally first. Someone else is downstream, right? And frequently downstream means drinking water for people, and having too much nutrients in water means that microorganisms are going to like it. And we don't want a ton of microorganisms in our drinking water, because that usually means bad stuff for us. So health-wise, bad stuff for us, bad stuff for animals that drink it, because there's too many microorganisms in the water. It also means bad stuff for fishes and anything that lives in the water, because what results from too much nutrients in the water is algae, and algae uses up all the oxygen in the water. Okay. And so you get what's called a dead zone, because there's nothing can live in it, because there's no oxygen in the water, because the algae used it all up, because there was tons of it in there, because there was so much nutrients in the water. Okay. You go out to the renarium right now. Our old renarium is just got tons of algae in it, and I've been slowly trying to knock it back. And one of the concerns is, so we've got frogs in there. We don't want the oxygen in the water to get so low that they can't survive in there. They need to survive. So that's certainly a concern. The biggest dead zone in the world is at the base of the Mississippi River, where it runs out. The Mississippi River Delta in Louisiana is the largest dead zone. It stretches hundreds of miles across the coast down there, and nothing can live in that water. No fish, almost nothing. If it's aerobic, breathe oxygen like the rest of us. They just can't live in that water. And so as a result, not a good place to live. And all of the fishermen that are in Louisiana, they have to go way out in order to find, stuff to catch. Okay. Seafood to catch and stuff like that, because things just can't handle the lack of oxygen. Where's all of those nutrients coming from? The breadbasket of our country, the Great Plains, where there's tons of corn and rice fields and stuff, soybean fields, and all of that's getting over fertilized, and all of that fertilizer comes running down the Mississippi and out the Mississippi River Delta, and we result in a massive, massive dead zone. So heavy metal binding, I forgot to mention that. It can, so heavy metals can have a charge on them, and if they have a charge, guess what? That means that it can bind to the cations, or the ions that are in the soils as well. So all of those things are super important. Okay, so plants absorb nutrients from soil solution. We already know that. Cation exchange acts as a nutrient reservoir that can replenish the soil solution. So it's a battery, right? It's a life battery of nutrients, and as it gets diminished, it replenishes itself by how much it can hold. Yeah, it's kind of a rehashing. Anything else? Organic matter always improves. Cover crops can also help too, because it keeps water in the soil. And binding the soil together with cations, pluses and minuses, helps hold and reduce soil, because it's like a little magnet holding each other together. And of course, then it helps you also manage your soil pH. So, all right. So I think we've covered most everything with cation exchange. CEC measures soil nutrient holding capacity. So if you got a good CEC, you're holding your nutrients. Clay and organic matter increase your CEC. High CEC soil nutrients store better, and CEC affects soil management big time. Okay, any questions on CEC? Kind of an important topic, really is, when it comes to soils. So hope you'll go back through this and rehash it. We got a few minutes. Let me show you this video that I think is a good summation to help you remember. Remember this stuff. It's coming out. Okay. No. See ya.